Good morning, everyone. Well, at least for me, because it's 6:20 a.m. So here we go. It's some math. Right now we're doing 4.1, Introduction to Exponentials and Logarithms. Pretty much we're going to look at the basics, but we're also going to interpret graphs. Okay, so we're going to do both. So the first thing, let's talk about exponents and their properties. Of course, exponent means the base multiplied by itself that many times, okay? And then here, 16 to the 1/4 is 2, since 2 is greater than 0, and 2 to the 4th is 16. So we can interpret this, of course, going back and forth, right? This is the 4th root of 16. So what do you multiply by itself 4 times to get you 16? Okay, so going backwards. The idea right here, though, is if n is even, then a to the 1/n, so the root, right, an even root, b to the n is a, okay? Whereas an odd one here, we have to remember, you're asking ourselves right here, what do you multiply by itself 3 times to give us -8? Well, a negative times a negative is a negative, right? Negative times a negative times a negative is a negative. So that's where that comes out, okay? So be careful with the odd one. When this one, I really want you guys to pay attention to. I think kids try to do things too much at once. I would separate it just like they show you here. So 8 to the 2/3. Yes, we could probably do this on our calculator, but we could do it separately when solving. So I'm going to take this as 8 to the 1/3, and that's squared. See how I separate? Because multiplication, power to power is multiplication. So now, if I knew 8 to the 1/3 is 2, now 2 squared is 4. Way different, easier to split it up than anything, okay? All right, so let's look at where we can deal with exponential and how it comes about in real life. So the value of a car can be modeled by v of x equals 25 times 0.8 to the x, where x is greater than or equal to 0 is the age of the car in years. So x is the age of the car in years. And v to the x is the value in thousands of dollars. Find and interpret v of 0 and v of 7. So v of 0 says we plug in 0 for x. Now anything to the 0 is always 1. 1 times 25 is 25. Now, what does that mean? Well, that means at the purchase, right? Because you purchase the car at 0 years. Purchase, so I say at purchase of the car. It is worth $25,000. Now, don't forget, it did say 1,000, so we want to make sure we interpret that correctly. Okay. Now, v of 7. So we plug that in, we get 25 times 0.8 to the 7. Now, by the way, guys, remember PEMDAS. If we were to do this by hand, you would be calculating the exponent first and then multiplying. Do not multiply the 25 times 0.8 and then to the 7. Does that make sense? Now, when you do that and you plug that in the calculator, we get 5.24288, and it keeps going. But of course, if we're talking about money, we only have to go out 2 decimal places. So we would say after, and then remember the x meant years, so 7 years, the car is worth $5,243. Okay. Now, I'm not going to say cents. I mean, it could say cents, but it says thousands of dollars. So let's just keep it in dollars. Okay. All right. Basic exponential function. So how it's represented. Okay. A function in the form f of x equals b to the x, where b is a positive real number, b does not equal 1, is called, excuse me, the exponential function with base b. Okay, so that's how many times it goes by, right? So here are some properties that we know. And by the way, why is it that we don't want b to be 1? Well, 1 times itself is just itself. So we're not really going to look at that. We're going to look at b being greater than 0, but not equal to 1, okay? So in your regular exponential, your domain is negative infinity to infinity, and the range is 0 to infinity. The graph of f has an intercept at 0, 1, which makes sense, right? Because if we plug in 0 for x, anything to the 0 is always 1. And the horizontal asymptote at y equals 0. F is a one-to-one function. If bm equals bn, then m equals n. Okay, so here's what happens. If b is greater than 1, then f is always positive and increasing. So what happens, guys, is on a graph, okay, now remember, it's always 0, 1, and it's always going to be increasing. Don't forget, we have that asymptote at 0. Okay, so it's going to look like that. Now, of course, it can move up and down, left and right. So this is just your basic, okay? Now, for b is between 0 and 1, it's actually going to reflect itself, okay? So we still have 0, 1, and we still have that horizontal asymptote, okay? And you can interpret it like that. Next one. All right, so here are your graphs, which I just sketched a little bit for you. So what we're going to do is we're going to analyze how we can graph these starting with the parent function and then go from there, okay? So example 2, graph to the x plus 1 minus 3 using transformations. So we're going to start with parent function, okay? The parent function, of course, is f of x equals 2 to the x. So see, that base stays the same and our x is in our exponent. So what we're going to do then is think about that we have a horizontal asymptote at 0, y equals 0, right? And then we have to think of some points that it might go through, okay? So I like starting with the graph. Now, you always want to interpret, though, because we know at 0 it's 1. So let's interpret -1 and 1, okay, and 2, okay. Now, if you don't want to do -1, you can always do it on your calculator, but I'm going to show you without it. So if I said 2 to the first, we would get 2. 2 squared, we would get 4. So of course, if we went backwards here, we're dividing by 2. So 1 divided by 2 is 1/2. So this is our parent function, and this is where it starts. So I should say y equal, not f of x. I should call this something different. We'll call it g of x right here. Okay, so now that we have f of x equals 2x minus 1, or plus 1, minus 3, let's talk about the movements. What does the plus 1 mean, and what does the minus 3 mean? Well, the minus 3 is on the outside, so we know that goes down 3, okay? And then here, when it's done to x, that is like your inside stuff. So plus 1, we have to think of the opposite movement. So it's going to be left 1. Okay. So how do we interpret that on a table? Remember, down and vertical stretches we do to y. So I'm going to go subtract 3. When I subtract 3, I get negative 5/2, negative 2, negative 1, negative 1. To right, or to the x here, I have to look at going left 1. Okay, always do the opposite to what I see. So I'm going to subtract 1. So I get negative 2, negative 1, 0, and 1. Okay. Now if I were to graph this, the one thing I do love is that the horizontal asymptote started at y equals 0. So what that means is that if I go up or down, that's where my horizontal asymptote is going. So I'm going down to 3. That's the first thing I would move. And now we can actually deal with our points here. So at negative 2, I'm at negative 2.5. At negative 1, I'm at negative 2. At 0, I'm at negative 1. And at 1, I'm at, what did I do? This. Oh, this is 1. Minus 3 would be positive 1. I knew there was something like that. All right. And at 1, it would be 1. All right, now let's interpret the domain and range. So as you can see, the domain does not change, right? We're still negative infinity to infinity. Now we have our range. Well, think of that horizontal asymptote. It went down 1. So that range, we're getting really close to negative 3, but never touching it. So it's a parenthesis. And then we keep going up to infinity. Okay, and now we need to label our new horizontal asymptote, which is at y equals negative 3. So be careful, always label that correctly. All right, cool. Let's go on to solving exponential equations with common bases using a one-to-one property. We begin with the observation that 2 to the x equals 8 means x is the power in which we raise 2 to get to 8. We adopt a special notion for this x value. It's called the logarithm. Okay, so log base 2 of 8 reads as, of course, what I just said, logarithm in base 2 of 8. Since we can see that 2 to the third is 8, we can conclude that log base 2 of 8 equals 3. Okay? So for y is greater than 0 and b is a positive constant other than 1, log base b of y is called a logarithm base b of y and the power of b that gives y. Okay? It is common to say log instead of logarithm, as you can hear me saying throughout the whole thing. And we can switch these back and forth. So remember that b is your base, x is your exponent, and y is what we expand to, okay? All right, because the connection between logarithms and exponentials, we must have b is greater than 0 and b cannot be 1. So we went over that with exponentials. So if that goes for exponentials, that also goes for logarithms. Okay, since the range of the exponential is the set of positive numbers, we must have the same condition. Okay, so what we are actually going to do when we interpret this, and I mean, they don't actually say the conversion yet, but we're just going to convert it. Because I don't know about you, but it's easier to solve things in exponential and see it. So what I'm going to do is actually change this. I'm going to use what they have for a property down here to do it. Okay, I'm going to change that form right now. So I'm going to write my base. My base is 3. What we don't know is our exponent. So I'm going to put an x there. But we do know that when we expand this exponent, we get 81. Okay. And then we ask ourselves, 3 to the what is 81? And in your calculator, you can go 3 times 3 times 3 times 3 until you get 81, and you find out that the value is 4. 3 to the 4th is 81. Okay, let me do the same thing for B. So we get 5 to the what is 125. What I want you to keep in mind is that since it's a fraction, it must be a negative exponent. Okay, now how I interpret that is I kind of ignore the fraction at first, and I say 5 to the what is that denominator? 5 to the second is that denominator. Now I have to go back and say, hey, it was a fraction, so it's a negative value. Okay, now this one's going to be a little bit trickier. So I have 8 as my base to an exponent we don't know equals 4. Well, here's the thing. 8 times itself so many times will not give us 4. 4 is not one of those perfect squares and cubes and all that stuff. But there is a number that they both have in common. What is it they both have in common? 2. 8 is 2 to the third. And then, of course, we still have that x. And 4 is 2 squared. Now, let's use our exponential properties. Power to power means we multiply. So this is 2 to the 3x equals 2 squared. Now, what this means is since they have the same base, we can kind of ignore it and realize that 3x should equal 2, and we solve. Divide by 3, and we get that this equals 2/3. Yes. All right. So if they do not have nice bases like that, you're going to have to change the base, okay? Now, we're just going to convert of what this looks like. It just wants us to change the form so we know what we're doing. So just keep in mind that the 1/2 is the exponent. 6 is the base, so 6 to the 1/2 is square root of 6. Now we look at that, does that make like a true statement? Did I just say like? Does this make a true statement? Well, yeah, 1/2 is the square root, right? Excuse me. Now let's do this one. This one, though, we're going to change in the log. So remember, we say log. We talk about the base. The base is 10. Now remember, it equals the exponent. So that means 1 over 1,000 goes inside. Ta-da. Okay. Now again, we're going to do some more solving. It's going to get more in depth, but we're going to use it by changing the form. Okay. So we get 3 to the 4th equals x. This one's really nice, right? And why did I put 8? X. Because all we got to do is put it in the calculator, right? So we get x equals 81. That one was nice. This one we're going to have to do a little bit more algebra. We have our base is 2, our exponent is 3, and we have x minus 1. So let's solve. 2 cubed is 8 equals x minus 1. So x equals 9. Okay? Remember, it's what x makes, when we're solving, it's what x makes that statement true. And one of the things you need to do, and you'll see in the next coming problems, you need to plug back in your answer to make sure it's an okay statement. Now, what do I mean by that? I mean that, remember that you cannot, your y value has to be a positive number, all that stuff, okay? And I'll show you in a few minutes. If we plug 9 in here, 9 minus 1 is 8. That makes a true statement. We're all set. Okay, so you do need to check your work. All right, before we get into more solving, we're going to do some graphing here. I think we're going to do more solving next in 4.2. So just basic solving there with converting, and now we're going to look at the logarithm graphs, okay? So a definition of the form of log base b of x, where b is a positive real number, b is not equal to 1, and x in this case has to be greater than 0. Why is that? Because, let me highlight this instead, the log and the exponential functions are inverses of each other. That's why. Okay, so what does that mean really quick? I'm going to put this on the side. So remember our exponential, and I'm going to have my exponential in purple. Remember, it went through 0, 1, and it had a horizontal horizontal asymptote at y equals 0, right? Well, logarithm, because they're inverses, remember that inverses reflect over y equals x. Okay, so I'm going to reflect it. That means the logarithm would then have a point at 1, 0, and its asymptote would actually be now vertical at x equals 0. And we've got this. Okay, so exponential log. All right, so here's some properties. So remember with the exponential, our domain went from negative infinity to infinity, and our range went from 0 to infinity. Well, that changes for our inverse. And also changes our x and y, right? That's the idea of an inverse, changing x and y, okay? So just down here, if b is greater than 1, we look at our log, and then if b is between 0 and 1, we got it kind of going. Reflecting is the word I'm looking for. Okay, so how do we interpret that when we graph? All right, so of course we are going to start with our parent function. So I'm going to say g of x equals log base 2 of x. Now, remember that if I was thinking this is the inverse of 2 to the x, okay, I'm just thinking that. Remember that we change our table, our x and our y's. So if we go back to the, excuse me, the other page with our table, remember how we had for x's, we had negative 1, 0, 1, and 2. Well, if we switch that around, that's actually our y's. So we're going to go negative 1, 0, 1, and 2. And remember, our y values on the exponential were 1/2, 1, 2, and 4. So now again, switched 1/2, 1, 2, and 4. Okay, so lots of times, guys, if you're making a table for a logarithm, the easiest thing to do is think of the exponential, because it's easier to find the exponential coordinates, and then flip your x and y. Okay. All right, so let's look at this graph. What happens? Well, on the outside here, we're subtracting 1, so we're going down 1. And we're going to the left 3. Okay, so let's interpret that on our table. Down 1 means we're going to subtract 1 from our y value. And left 3 means we're going to subtract 3 from our x. Remember, do the opposite. So we get negative 5/2, negative 2, negative 1, and 1. Okay, now let's talk about our asymptote. Now in this case, remember for a log, we're going to do a vertical asymptote. Okay, so it's x equals. It started at x equals 0. Okay, and that was our vertical asymptote of our parent function. So if we're talking about x, we're actually talking about left or right. We're not talking about up and down. So if our left and right is what affects the asymptote here. So in this case, we're going to go left 3. So our vertical asymptote is at -3. Let's graph our situation. So 1, 2, 3. Let's do our vertical. Okay. Now let's plot our points. So we have a -2.5, -2, -2, -1, -1, 0, and 1, 1. So if I connect them, these go down to the asymptote, and these will curve off. Now let's talk about our domain and our range. Our domain, how far left does it go? Well, it's getting really close to -3, and it's going to infinity. And our range is all the way down, and our arrow, as much as this is sliding off, it will keep going off, so it's infinity. All right, one more graph, because of course it wants you to do something tricky. The good thing is we're still in the base of 2, so I'm just going to use our parent function table that we used above. So we get 1/2, -1, 1, 0, 2, 1, 4, 2. Okay, let's talk about what this happens here. So we are adding 1 on the outside. Adding 1 means going up 1. If you want, you could have rearranged that to realize it was in the back, so that way we don't get confused like that. Okay, now with a negative on the inside, what does that do? Well, negative on the inside reflects, but it reflects where, guys? It reflects the y-axis. Okay? So let's interpret that with our table. Up 1 means we add 1 to y. So I get 0, 1, 2, and 3. Reflects across the y-axis means that we multiply our x by -1. So -1/2, -1, -2, and -4. Okay, so remember that our asymptote deals with left and right, right? So the original asymptote here, the vertical asymptote, was x equals 0. Now, did we go right or left? No. So our new vertical asymptote is still x equals 0. Okay, so I'm still going to put x equals 0. Now I'm going to plot my points. Oh, I just colored my hand. So -1/2, 0, -1, 1, -2, 2, -4, so 1, 2, 3, 4. Oh, this should be 2, not here. Sorry, guys. 1, 2, 3, 4, 1, 2, 3. There we go. And if I put that together, that goes here, and this comes down. So as you can see, it did that reflection, right? And it moved it up to that point right there. So now if you think of domain and range, so domain, well, how far left does it go? That arrow tells me it keeps going to -infinity. And of course, we're getting very, very close, but not passing to 0. And the range, how far down does it go? Well, that arrow keeps telling me it goes down. And this arrow tells me it keeps fluctuating up. Ta-da! All right, guys. You can do some practice now, and then we'll get into more logs and exponents as we go through this chapter.